let's look now at an application of geometric series to repeating decimals. Suppose we want to write the repeating decimal 0.66666 with an infinite number of sixes as a fraction. We can actually write this out as a geometric series. This is 6 over 10 plus 6 over 100 plus 6 over 1000, etc., etc. And this is a geometric series. So we have 6 over 10 plus 6 over 10 squared plus 6 over 10 cubed. And the a is the first term, which is 6 over 10. The r is the second term over the first, which is 1 over 10. And the sum of this series is equal to a over 1 minus r, which is 6 over 10 over 1 minus 1 over 10. This is 2/3, which is something you probably already knew, but perhaps you didn't know exactly how to calculate it. Let's try another one. Suppose we have the decimal which starts to repeat after a certain amount of time. So let's say 1.521212121. How might I calculate this as a fraction? Well, it's 1.5, which is the non-repeating part, plus the repeating part, which is 21 over 10 cubed, plus 21 over 10 to the 5, plus 21 over 10 to the 7, etc., etc. Now the part other than the 1.5 is a geometric series, and I can find its sum. The a is the first term, the r is the second term divided by the first. Just to be sure, I should check that the sum from 1 to infinity of a times r to the n minus 1 gives me the same expansion as I have above, and I have that adds to the fraction 21 over 10 cubed over 1 minus 1 over 10 squared, which is 21 over 990. So my fraction is 1.5 plus that, or 3 over 2 plus 21 over 990, and I can add those two fractions, and I get 251 over 165 after I cancel.